Okay, so today we are going to start modeling with continuous random variables. Okay, and not only that, this section, as you have seen in your detailed syllabus, whatever given to you, the section we are covering is the special distribution, and after that there will be a function of random variable. So we will not do these two things separately. We will cover everything, but we will not do these two things separately. We will do simultaneously, intertwined. Okay, so let us start from here. Any query regarding the thing, whatever we have covered so far? So almost all necessary discrete distributions we have covered. Today let us continue with the continuous modeling with continuous random variables. So okay, so first of all, we will consider uniform distribution taken for granted, as I have told you. And we will try to see how we can relate everything from uniform, and at the end of the day how we can come back to uniform, because that I have told you, that is the basis of the possibility of generating random number through computer. And that has given the flourish of all these subjects, whatever we are doing, that all simulation, Monte Carlo simulation, Markov chain Monte Carlo simulation, as well as your whatever machine learning and blah 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 data science, whatever is happening nowadays, you are able to do only because of this fundamental idea. So let us start with uniform distribution. So let x follows uniform 0 1. This is the God distribution. I mean, from everything comes from here. So now screen is blurred. Is it not visible properly? Hello?
Sir, between times it gets blur and sometimes it is visible properly.
Then it is an internet problem, man, beyond my control. Okay. Yeah. And the weather is bad. There is a high chance that internet will not be that good. Although I'm using the institute connection, not any private connections. Let us see. Okay, now define y equals to a plus b minus a into x, where uh, a is less than b, real number. Okay. Now the job is find the CDF and PDF of y. If you know it's CDF and PDF, then rest of the thing you will know immediately. No problem. So what to do? I am showing you. I think we have done the similar thing earlier. I am just repeating this thing for in general. We have done an example that y equals to 0.5 into x. That example we have done in our class already. So this is a general version. So So y belongs to A to B. Okay. Now, if y small y is probability y less than equals to small y when y is here, that means probability A plus A plus B minus A into x less than equals to y. It is blur for everybody?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Yeah. So let me check because I have what can I do? Okay, so let me use the LAN. What can I cross check from here? Let us see if everything is opening properly. Yeah, now okay. Now it is sharp, but the contrast is also more. Let us see whatever is our purpose, whether it is serving. Yeah, please check. Is it okay?
Now it is blurred.
No, sir. Sir, due to three similar screens, it's taking time to come to us.
I didn't get you. Please say again.
Like your camera is on, then the other camera is also on, and PDF is also being shown. So these three things are taking much internet to come, sir. Like they are
But
requiring much speed,
I'm
and speed is
just
not
sharing
available.
the screen. I'm not sharing three things together. Okay, I can put the camera off. That is not a problem for me. But
Sir, you are sharing your whole screen, so that is not a problem, I guess.
yeah, that is not a problem. I'm just sharing whole screen. I'm not sharing three windows. But I have done the focus of this thing already.
Yes, sir. Even the PDF is blurred.
Then how can I support you, man? I am just using the LAN connection of institute. Nothing better option is to with me.
Sir, can you try running a speed test? Like we can know what is the ping. Maybe the problem is ping, not speed.
So where to do the speed test? I don't know.
On any browser.
Speed or any browser.
So now this is
Sir,
the
you can search a speed test.
now the blank page.
Yes, sir, it will come.
It's taking a lot of time, sir.
So you could look out for fast.com also. That's a more faster.
So right now the screen is very clear, but whenever you are sharing that page, everything is become blurred, getting blurred.
Yes, sir. It's blur again.
Blur.
Blur. Wow.
Sir, now it's good.
But
All
some
blur.
Clear and blur, sir. Alternative things.
This. So just give me 2 minutes. Let me restart the computer. Okay. Let me restart the computer and let us see if there is something wrong.
Pairing successful.
Yeah, please check it now. Am I audible?
Yes, sir.
Yeah. Now, what is the situation?
It is clear, sir.
Okay,
Yes.
then good. Good. Yeah. Okay, so let us continue. Should I put the camera on, or if it is off, it's okay?
So let it be off.
Okay, no problem. Yeah. So here you can see that we are considering that x follows uniform 0, 1, y equals to a plus b minus a into x, and we are interested to find out the CDF and PDF of y, that means the distribution of y, and y can take value between a and b from this relation. So probability y less than equals to y is, you can replace capital Y by this. So now you can write probability x less than equals to small y minus a divided by b minus a. See, this quantity is lying between uh, 0 and 1. So already you know the CDF of x. So it is y minus a by b minus a. Okay, so this thing will happen when y belongs to a to b. So I have to write, okay, 0 when y is, you can make it close, less than a, 1 when y is greater than b. Any doubt? So this is the CDF.
Sir?
And PDF, it is continuous valued random variable. So you can differentiate it and you will get 1 by b minus a when y belongs to a to b, and 0 otherwise. So now quickly tell me what will be the expectation of y. What will be the expectation of y? Yes, go ahead.
Sir, a plus b by 2.
A plus b by 2, because it is very easy. As this is expectation of a plus b minus a into x. So as a consequence, a plus b minus a into half. So this is a plus b by 2. And what is variance of y? Again you go by this variance of a plus b minus a into x. What is the variance of a? That is 0. B minus a into x is b minus a whole square, variance of this quantity, variance of this only, b minus a whole square into variance of x. What will be variance of x? X follows uniform 0, 1. Variance of x? Bolo, quickly.
1 by 12, sir.
Yes. B minus A whole square divided by 12. So this is the mean and variance. Okay. Homework for get MGF of Y. Again, to get
Sir?
M, yes, yes.
Yes, sir. Can you say how to find the variance of x here?
No, I didn't get your point. Please say again.
Yes, sir. How to find variance of x here?
Variance of X follows uniform 0 1. Go by definition. Expectation of X square minus expectation of X whole square.
Okay, sir. We will take integral x square.
Yeah. Just simple. Okay. The way we need to, again, you can use the construction to get the moment generating function of y also. So let me just tell you here that MGF of y, so MYT is expectation of e to the power ty is same as expectation of e to the power a plus b minus a into x whole multiplied with t. So it is expectation of e to the power at into e to the power b minus a into t into x. Okay, so as a consequence, what will you get is expectation of e to the power at first it will come, then moment you can see that expectation of e to the power b minus a into t into x. So I can write this quantity as m x t into b minus a. Check whether you have any difficulty with this notation and present. E to the power ty, y I have written, then a into t, that is a product term coming out, no random variable here. Then rest part is b minus a into t into x. So moment generating function definition is expectation of e to the power t into the random variable. So this is the constant multiplier here, then x. So you can treat it is a random variable, the moment generating function of x evaluated at t into b minus a. So now it is your job to get the moment generating function of uniform 0 1, and there whatever t should be replaced by t into b minus a. You will get the answer. Okay, so that is the easy way. Here, as you have got, you go by the relation, then replace the expectation of x. Here you go by the relation and replace the variance of x. Similarly, you go by the relation and there you replace t by the t into b minus a. That will be all. Okay. So before we go further, let us try to see that. I think we have a diagram for it. Yeah. So suppose this is the uniform 0 1, and then I can choose different values of a and b such that you can have a different distribution of uniform. So here I think the second one is A is chosen as, so this is uniform 0 1. You can see data generated from uniform 0 1. So histogram, when you plot, it will be up and down, doesn't matter. If you increase the number of sample size, it will be matching with this red line. And then A is chosen 2.3, B is chosen 5.8. So now that distribution, So from 2.3 to 5.8, now it is a more flat distribution. So if you compare that, this is the uniform 0, 1, this red line you can see, and this broken line, this distribution is from 2.3 to 5.8. So this is how it will change. Now if your B minus A, that already we have discussed, if B minus A is less than 1, then definitely you can see that this quantity will be greater than 1. So PDF can take value larger than 1, what PMF cannot take. Okay. If B minus A is less than 1, this PDF can take value larger than 1. Okay. So this is all about the uniform distribution. Anywhere you need to use uniform distribution, you can go by this. So here the general name is, we are studying uniform 01 or UAB, uniform AB. That is what we have studied. Now we are going to introduce another random variable. Again, we are starting from uniform 01. So let X follows uniform 01 and Y equals to -1 divided by lambda log base E 1 minus X, where lambda is greater than 0, and find the distribution of Y. So can you quickly tell me the CDF and PDF? Again, the technique is same. So what will be the possible range of Y? What values Y can take?
The 0 to infinity.
0.
Yes.
0
So,
to.
yeah, Y belongs to 0 to infinity. Okay, then if Y is probability Y less than equals to small y, same technique. When the change will be needed, I will tell you. As long as you can do this way, you go by this way, this is the, safest method. There will be no mistake. So then you write the relation -1 divided by lambda log E 1 minus X less than equals to small y when Y belongs to 0 to infinity. Probability of that. So if you do the side change and all those regular stuff, you will get probability X less than equals to 1 minus e to the power minus lambda Y. Check. Is it okay?
Yes, sir.
Okay, very good. So again, this quantity lies between 0 and 1, and X follows uniform 0, 1, already you know. So this is 1 minus e to the power minus lambda Y. So the CDF is FYY 0 if Y less than 0 or less than equals to 0, whatever you write. 1 minus e to the power minus lambda Y when Y greater than 0. Okay. So what will be the PDF? Tell me.
The lambda e to the power minus lambda y.
Lambda e to the power minus lambda y. When y is greater than 0 and 0 otherwise. Okay. Now, now, so this distribution is known as exponential distribution, and it is usually denoted by this, that y follows exp lambda. It doesn't mean e to the power lambda. Okay, remember this thing. This is known as exponential distribution, and the notation is this, that y follows exp lambda or capital exp lambda. It doesn't mean e to the power lambda. It follows, when we write y follows exponential distribution, that means it has CDF this, it has PDF this. Okay, so this is one thing. So when we use this distribution, so this distribution is used again for waiting time distribution. So exponential distribution or random variable is used to model waiting time. So in general, say lifetime of a machine. So a lifetime of a bulb or fan or computer, something like that. Then how long you need to wait in a server to get the response. Maybe you are going for the passbook print in a bank, or you have sent a mail, you are waiting for its reply. So service time. And you are waiting for a lift to come down and take you to the place. So all these things you can model with exponential distribution. So you can use to compute its expectation. So sorry, expectation of y. You can compute with this formula also, that either you go by y fy dy 0 to infinity, or you can go by this formula, that integration probability y greater than equals to t 0 to infinity dt. Okay, so whatever way, quickly calculate it and tell me. This is the thing, you know, for non-negative random variable it will hold. Again, it is another interesting, that inter-arrival time of customer in a queue. So all these things are very nicely modeled by exponential distribution. So please tell me its expectation.
One by lambda.
1 minus
1 upon lambda. Variance will be 1 upon lambda square. And a homework I'm leaving that get MGF of y. Okay, so I'm not going for this one because that is at this moment it is not a special interest of us, but you need to know. Okay, so here this lambda, well, let me again tell you that many books use different notation. Instead of having the expression in this way, they get the expression 1 upon lambda e to the power 1 of y by lambda, y divided by lambda. So you can see that if lambda is the parameter, the mean will be the reciprocal of that and variance will be the square of that. So you need to know that what is given. There are other alternative way to write this thing, that y follows exponential distribution with mean 1 upon lambda. So often people write in this way that mean is 1 upon lambda, that means parameter lambda, that means PDF is this or CDF is this. So different books you will find different notation. You have to figure it out what is the PDF or CDF will be. So in general, lambda is the parameter and lambda is the scale parameter, or maybe say here we can say that it is a rate parameter here. So if it is rate lambda, mean is 1 upon lambda. So it is a rate parameter. And you can see that it is very trivial that if your rate is high, then you need to wait less. Is it clear? That if your rate is high, rate of occurrence of some event is very high, you need to wait very less amount of time to get it. And that's why it is coming in a very natural way. It is reciprocal of the rate. So your expected waiting time is less. So now can you tell me any example what you have already seen? I am sure that all of the science background student has come across the example of this exponential distribution in your physics or chemistry book.
Radioactive.
Yeah, please say.
Radioactivity.
Hello, please say.
Radioactivity.
I'm not able to hear.
Sir, radioactivity.
Yeah, radioactivity. Waiting time, half-life time. There you have seen this distribution. And not only there, you can use this distribution for many other general ways, which are useful for modeling the data. Okay, so now we are going to see a very nice and interesting property of this distribution. And that property, well, it is a nice property. At the same time, because of that property, this distribution is I mean, that is also sometimes the disadvantage of this exponential distribution. So please try to compute this conditional probability that this thing that y follows exponential lambda, then probability y greater than s plus t given y greater than t. Okay, so what does it mean? That the event has not occurred up to time t, and event given that the event will not occur up to time s plus t. Okay, so if you consider 0 here, t here, s plus t here. So up to this point of time, so t, okay, if you use equal to sign, not don't use equal to sign, doesn't matter. So up to time t, the event has not occurred. So here the event has not occurred, and you are interested to see that even up to time s plus t, the event will not occur. So this will not occur and has not occurred. So up to time t it has not occurred, up to time s plus t still it will not occur. So please tell me what will be the thing. So you go by the fundamental definition of conditional probability, that probability y greater than s plus t intersection y greater than t trivial divided by probability y greater than t. So what is the intersection of these two parts?
S plus t.
So probability y greater than s plus t divided by probability y greater than t. Okay. Now if you go by the definition of CDF, so this is probability y less than equals to small y. So from there you can write it is e to the power minus lambda s plus t divided by e to the power minus lambda t. So it is e to the power minus lambda s, which is probability y greater than s.
So should
So
it
what?
be 1 minus e to the power minus lambda s plus t by 1 minus e to the power minus?
No.
Because in CDF we say
CDF say y less than equals to small y.
yes sir. Here y less than equal to small y, but here we in the
Here
question we
y
want.
is greater than this.
So it is 1 minus p of y less than.
One minus this.
Okay.
Okay, so here you notice the interpretation that although I was waiting up to time t and found nothing, then I was waiting up to s time more, and the probability is same as waiting s time starting from the 0. Is it okay? That it is same as I have just waited time s and I got no event. It is just losing all the information that I have already waited up to time t. So that is that t has no longer any impact on here. It is considering afresh from here to here as if I am starting from 0. So this property is known as the memoryless property. So this property is known as the memoryless property. Okay, of exponential distribution. This is a very fundamental property. Now I can give you a homework what you can verify, that say Z follows geometric P, then probability Z greater than, here S and T both are positive. Okay, Z greater than M plus N given Z greater than M is same as probability Z greater than N. So this is memoryless property holds for exponential distribution in continuous case and for geometric distribution in discrete case. And I have already told you when we have introduced the geometric distribution that we can model the waiting time in discrete sense through geometric distribution. So this is also a waiting time distribution, exponential. Geometric is also waiting time distribution in discrete. Both of them has memoryless property. Is it a coincidence or there is some connection? Do you think that we will be able to find out any connection or it is just a coincidence? What is your guess? First, let me know. Is it possible to find out any connection between Y and Z, or it is just a coincidence? Okay, so try to figure it out. Okay, let us consider this thing that Y follows exponential lambda. Okay, and I am defining, say, Z equals to greatest integer function or the box function of Y. Anybody doesn't know this greatest integer value function? Please let me know, otherwise I have to define it. If you know, it is very good. If you don't know, then let me know, I have to define it. Is it okay to all of you?
Yes, sir.
Okay.
Yes, sir.
So greatest integer value function. Now my suggestion, get the distribution of Z. And this is a very natural thing because, say for example, any event, maybe say calls are coming to a telephone exchange or mails are entering in your Google server account, then your institute server account, then your account in this way. So every time whenever the event occurs, you may not get the information at that point of time. So maybe the information is collected of 1 minute interval and sent to you, or 1 hour interval or sent to you, or 1 day interval or sent to you, something like that. So this is a very natural construction. So whenever in continuous sense event will occur, you may not receive the information then and there. So there will be discretization and you will get the information after that. So what are the values Z can take? Z belongs to Y is exponential, so Y can take value from 0 to infinity. And Z, what are the values Z can take?
They're non-negative integers.
Non-negative integers, 0, 1, 2, and so on. Okay, so what is the probability Z equals to 0?
They're 0.
Hmm?
Because the set is infinite, so probability is 0.
Oh my goodness. Z has a relation with Y, right?
Sir, Y
Probability of y less than 1.
yes,
So
sir.
probability of Y less than 1. So probability Y greater than 0 less than 1. And what is that number? 1 minus e to the power minus lambda into 1. Is it okay?
Yes.
What is the probability Z equals to 1?
1 to 2.
E minus lambda minus e power minus 2 lambda.
E to the power minus lambda minus e to the power minus 2 lambda. So can I write in this way that it is e to the power minus lambda into 1 minus e to the power minus lambda? Is it okay?
Yes, sir.
Now in general, probability z equals to r. What it would be?
E power minus
E
r
power
lambda
minus lambda.
1 minus e power minus lambda.
R lambda minus e to the power minus r
Minus
plus
r plus 1 lambda. Yes, sir.
lambda. So e to the power minus r lambda 1 minus e to the power minus lambda. Is it okay?
Yes, sir.
So from here, can we write this thing that probability z equals to r in general, that is e to the power minus lambda whole to the power r into 1 minus e to the power minus lambda when r belongs to 0, 1, 2 up to infinity and 0 otherwise. Is it okay? So now please tell me what z follows. What will be the distribution of z? You already know.
Geometric distribution.
Geometric distribution. Parameter?
E power minus lambda.
E power minus.
No.
1 minus e power minus.
1 minus e power minus lambda. So this is the probability of success. This is the probability of failure. So geometric P. So this is Q. Q to the power R, and this is P. Is it okay? So there is a connection between this exponential distribution and geometric distribution. It is just a natural discretization of this continuous random variable. And well, there is also a connection can be constructed from where you can go back from geometric to exponential, but for that characteristic function is needed. We will not be able to do in this course. So this is an interesting property and very much natural property, because you can see that all information then and there cannot be passed. So some information or event occurs, then maybe with 1 minute gap the information is transferred to another system, or maybe 1 day gap the information is transferred to another system. So all these things are very natural, and this is a very fundamental construction to move from exponential to geometric. Okay, any query?
Sir,
Okay, yes, please.
sir, if z lies between 0 to infinity and it can take value of only integers, so sir, what is the probability of z being 0? Sir, isn't it 0?
Look, it depends on how the distribution is constructed. I am not assigning uniform probability to all of it, and that is not feasible. On an infinite set, countable or uncountable, you cannot assign uniform probability to each of it.
Okay, sir.
Is it okay?
Yes, sir.
Okay. So another thing So now try to see another connection. We will talk about it little bit later, but anyway. So if say W follows a Poisson process with rate lambda, what is the probability that no event up to time no event up to time say small t? What will be this one? If W follows a Poisson process with rate lambda, what is the probability no event up to time t? You have just seen in yesterday's class. No event up to time t. Poisson process with rate lambda.
E to the power minus lambda t.
So it is e to the power minus lambda t. And if I say that y follows exponential distribution with rate lambda, and what is the probability no event up to time t?
E to the power minus lambda t.
Again e to the power minus lambda t. So here you can see that there is a connection. Okay, so we are not going to establish it rigorously, but just let me tell you, if there is a Poisson process, then the inter-arrival time between two events follows exponential distribution. Okay, so just let me give you as a note. I am not going for the proof that if that requires conditional random variable. When we will do, maybe we will come back there. So if there is a Poisson process with rate lambda, then the inter-arrival, that means inter-arrival time, that means the time between two consecutive events, time between two consecutive events follows exponential distribution with rate lambda. So it is exponential distribution with rate lambda, and it is Poisson process with rate lambda. So that means you start from here 0, first event has occurred at T1, second event has occurred as T2, third event has occurred at T3, fourth event has occurred at T4, in this way. So Poisson process is going on. So this in the length of this interval length of this interval, this interarrival length, they will follow exponential lambda. So T1 or maybe say T1 will follow exponential lambda. T2 minus T1 will follow exponential lambda. T3 minus T2 will follow exponential lambda, and they all will be independent from the construction of Poisson process. So in this way it will go. So this is a very fundamental construction of the Poisson process. Now from here, suppose you are considering this example. Suppose you are considering a queue that first at time 0 or maybe say 10 o'clock the gate of the bank opens. Or so first customer arrives at time T1, second customer arrives at time T2, third customer arrives at time T3, fourth customer arrives at time T4, and the interarrival times are following exponential distribution. Okay. So what will be the distribution of the, say if you want to know that what is the time of the arrival of the kth customer. So when interarrival times follows exponential lambda, then what is the distribution of the arrival time of say kth customer. So maybe 10th customer, maybe 15th customer, or 50th customer, doesn't matter. But the underlying assumption is that the gap between the arrival of two successive customers, that follows exponential and IID. Follows exponential, rather I should say IID exponential. They are independent also. So that can be modeled with gamma distribution. Okay. So gamma distribution has a PDF in this way that say we can write. Okay, so in general, let me write that if we write z equals to sum over I running from say 1 to say r yi, this follows gamma r lambda when yi's are IID exponential lambda. And exponential, let me just write down the PDF of gamma distribution, you will be able to see the thing. So the gamma distribution R need not be an integer. Okay. So the PDF of gamma distribution, so when Z follows gamma, say I can write R lambda or alpha, let me write down in general form. So Z follows gamma alpha lambda. This is the way many books write. So F Z, or I hope all of you are familiar with gamma function. So from there, e to the power minus lambda x, x to the power alpha minus 1, lambda to the power alpha, gamma alpha. When x is greater than, z, I have written z. So when z is greater than 0, as well as alpha and lambda both are positive, 0 otherwise. So this is the PDF, and you know it is a gamma function. If you integrate out 0 to infinity, you will get 1. There is no problem with it. So remember that alpha is known as the shape parameter and lambda is rate parameter. Alpha need not be, this is positive, but need not be integer. Okay, integer, being an integer is not needed, but positive is needed. Now you can see that if you have alpha equals to 1, so if alpha equals to 1, then what does z follow? Say, so it will follow exponential lambda. So here you can see that y following exponential lambda. So exponential lambda is equivalent to say gamma 1 lambda. Any query? Hello. Any query?
Sir,
Yes.
sir, if alpha is not an integer, sir, then how we will calculate alpha factorial?
Okay, sorry. Wait, let me just make this. Prasad, go ahead, please turn off your mic. From where? Okay, so factorial, well, let us talk about it. So at least this is convinced from the PDF, right? And gamma distribution also have the additive property. I will come to your question that if say Z1 follows gamma alpha 1 lambda, Z2 follows gamma alpha 2 lambda, and they are independent. Remember the lambda should be same. Then Z1 plus Z2 follows gamma alpha 1 plus alpha 2 lambda. This holds, and how can you prove it? Either by the PDF, no need to go by that, you use MGF to prove it. It is very easy to prove by MGF. So
Sir,
yes.
Sir, if alpha
Hello?
can't means alpha can also be a real number, positive real number. So how we
Positive.
are gonna calculate it, sir?
So gamma alpha.
Yes, sir.
So what is suppose if it is integer.
Yes,
Okay,
sir.
so
So we will
let
find
okay, so let alpha belongs to say
z plus
natural number. Okay, so then what you write for gamma alpha?
alpha minus 1 factorial.
So alpha minus 1 factorial.
Factorial.
Okay, so it is also written in this form alpha into gamma
Gamma
alpha
alpha
minus
minus 1. Yes, sir.
1, right?
Yes, sir.
So this is true in
Sir,
general. So
alpha
even
minus 1
Sir, alpha
into
minus 1, gamma,
yes,
alpha
sir.
minus.
Alpha minus 1, gamma alpha minus 1.
oh sorry, alpha minus 1 gamma alpha. Right. Alpha minus 1 gamma alpha minus 1. Yeah. So this is in general true. Alpha minus 1 gamma alpha minus 1. And this is how you need to go to expand until you as long as you have the alpha minus 1 alpha minus 2, this thing will remain positive. You keep on doing this.
Okay, sir.
Okay, so this is true in general. This is true in general. In particular, for integer, you have this facility to write as a factorial. And this comes from that if you do the integration by parts of thing, you will get this relation. Okay, so from here, again, let us go back to this. If yi's are following IID exponential lambda, then now with this additive property, it is trivial that sum over yi, I running from 1 to r will follow gamma r lambda. Any doubt? With this additive property, so for each yi you consider gamma 1 lambda, sum of such IID gamma 1 lambda r times will give you gamma r lambda. Any query? Okay, so if not, then it is very good. So quickly tell me, what will be the expectation of say let us call that when z follows gamma r lambda, z follows gamma r lambda, and for the time being assume r belongs to natural number, then what will be expectation of z?
R by lambda.
R by lambda. What will be variance of z?
R by lambda
You know
squared.
r by lambda square. Now it is your homework just to cross check when z follows gamma alpha lambda in general, expectation of z is alpha by lambda, variance of z is alpha by lambda square. Well, alpha lambda both are positive. It doesn't matter. The form will remain same. Okay. So here I think yes, please.
The r by lambda square or r by lambda?
Square. Square. As we have done from Bernoulli to binomial, geometric to negative binomial, similarly from exponential to gamma. Okay. So how many distributions you have got so far which will follow the additive property? Whatever we have studied so far, how many of them you can think of that they will have the additive property? Can you please give the name?
The binary
Tell me.
distribution.
Binomial. Okay, good. Then
Sir, gamma distribution.
gamma 1, good. Other? Negative binomial, will it hold? Negative binomial R1P, negative binomial R2P. If you sum them,
Yes, sir.
yes, it will hold. Poisson, will it hold? Check Poisson will also hold. X1 follows Poisson lambda 1, X2 follows Poisson lambda 2 independent, X1 plus X2 will follow Poisson lambda 1 plus lambda 2. All proof will be very easy if you use moment generating function. Okay, so here it is graph of the empirical distribution from exponential. I think I have drawn data for lambda equal to from 0.2. So this is the graph for exponential distribution, and this is the graph for gamma distribution with alpha equals to 3 and lambda equals to 0.2. So if you add 3 exponential, you will get this gamma independent exponential. Okay, now we are going to, well, beta we should look, and then we will go for normal. So beta is a different kind. It has more importance theoretically than practically. So let me just give its interpretation as well as the PDF. For all of the random variable, having CDF is not an easy task. Say for example gamma, you will not be able to write a closed form CDF, but PDF is, well. Okay, so here, so we have, I think I have written gamma name and all those things. Okay, so here let us introduce beta. So beta alpha 1, alpha 2, or beta A we often write. So I hope, as you know, gamma function, you know also the beta function. So beta construction is something like this, that if say x follows gamma alpha 1 lambda, sorry, x1, x2 follows gamma alpha 2 lambda, and they are independent, then y defined as x1 divided by x1 plus x2, the ratio or the proportion you can think of. So this quantity is said to follow beta alpha 1 alpha 2. Proof can be done after studying multivariate, or sorry, joint distribution, we will do that proof. And you can also notice that y belongs to 0 to 1, because this is positive, this is positive, this is one part and this is the total. So y lies between 0 and 1. So advantage of this, when you need to model probability, say for example binomial p. Now if you want to assign some probabilistic structure over p, then beta distribution is a very interesting thing. And there are many other situations which at the well, let me give you this idea roughly, not so rigorous, that say for example stock market price. So you consider the 1 day observation, at when it opens the value is 0, when it closes the value is 0. Say for I am giving very roughly, not in a very rigorous way. In between some price is fluctuating or some variable is fluctuating, and where it will attain the maximum. It starts from 0 and it is returns at the end of the day, it returns to 0. But at what point of time, so entire day you can scale it between 0 and 1. The magnitude starts from 0, ends at 1 at 0. At what point of time it will attain the maximum, this kind of thing can be modeled through beta distribution. So it is a very important distribution. You will not find its application very easily in your rudimentary work, but if there are sophisticated probability techniques are used, then beta distribution is very important for Bayesian statistic and at the same time probability modeling. This is little bit sophisticated things comes into play, then you will see the application of beta distribution very well. And the general version of beta distribution, that means not only in this way, so a PDF, so let us call y, if y is y into alpha minus 1, 1 minus y into alpha 2 minus 1 divided by beta alpha 1 alpha 2. So beta alpha 1 alpha 2, you know that this is gamma alpha 1 gamma alpha 2 divided by gamma alpha 1 plus alpha 2. Again alpha 1 alpha 2, both are positive when y belongs to 0 to 1, 0 otherwise. So this is the density. So homework, or now you can tell me that plot beta half. Can you please tell me how will it look? How this curve will look? I am giving this one as a just as a result, because proving this thing will, from straightforward definition you can go, otherwise tricks are needed that we have not done yet. So expectation is similar, variance of y is alpha 1 into alpha 2 whole divided by alpha 1 plus alpha 2 square plus alpha 1 plus alpha 2 plus 1. This is not so. So can you please tell me how this beta half will look? This is a very interesting result. I mean, in advanced probability theory, beta half comes again and again. how will it look? Beta half half. Plot the graph. So tell me the PDF. What will be in the denominator? For beta half half?
Say pi.
Pi. Okay. And numerator?
Y to the power minus half times 1 minus y to the minus half.
So can I write y into 1 minus y? Is it okay?
Yes, sir.
Yes, sir.
So y belongs to 0 to 1. So how will it look? Probably you have not seen this kind of PDF. This is how will it look. All PDF you have seen, it is starting from 0, going up and then going down. And this is something upside down. That's why I have asked. So it is not a usual looking PDF, but anyway, it comes in your probability theory. Okay, so you get the CDF. Getting CDF is easy. For this one, you will be able to write down the CDF. So get the CDF. If you integrate, what will be the function? If you integrate this one, what will be the function? That you should be able to tell me. What is Fy
Sir,
is
2 times sine inverse under root y.
yes, 2 times sine inverse under root. This is the thing you will get. Otherwise, writing CDF of beta is not a easy task. Well,
Sir, divide by
after
pi
few
would also
days,
come.
pi will come, right? Yeah. So after few days, I hope time will permit, we will see that there is a connection between the CDF of binomial distribution and beta distribution, and there is a connection between the CDF of Poisson distribution and gamma distribution. We have not yet reached up to that level to establish that connection, but we will be able to do that, and I hope time will permit and we will be able to do that. This continuous evaluation is killing the time to deliver the thing, but anyway, as the time demands, we have to do. So let us now go to the normal distribution. I hope all of you have somehow, whoever done little bit of statistics in your 10+2 level, already familiar with normal distribution, but let us revise it and add something new to it. So normal distribution, which is, so now it is your time Give me example when you can use normal distribution. What values mu can take? Tell me. What are the possible values mu can take? Mu is the location parameter. And mu can take any real number. Sigma is the scale parameter. And sigma can take positive values only. Okay. So it is found, well, we will start from here, that let Z follows normal 0 1. So the PDF is given by e to the power minus z square by 2 root 2 pi. Okay. So from here you can add the location. So in this way, that say mu plus z is set follows normal mu 1 when z follows this, and mu plus sigma z will follow normal mu sigma square. So here this is also denoted by the standard notation. This is also denoted by phi z. Phi function is written by this formula, the PDF of standard normal distribution. So this is known as the standard normal, and these things are common in literature. Okay, now, and this is the PDF of standard normal. Now what one thing I can ask you to do, how this thing comes, the proof we will, the general proof we will do by the end of this section, transformation of variable, the general proof, but already we have done some similar proof which will take from PDF to PDF. Whatever we have done, we have gone from CDF to CDF, and then we have got the PDF. Okay, so from uniform 0 1 to uniform AB, uniform 0 1 to exponential, and then also we have seen the sine curve distribution long back, that everything from CDF to CDF, and then we have got to PDF. But if you transfer from PDF to PDF, then we need a result. That result we will study in the next week. But this proof we will be trivial after that. So before going there, can you please tell me how you can show that this integration will be 1? That this is a legitimate PDF. This is proposed by Gauss. So it is also known as the Gaussian distribution. So can you please tell me how this quantity will be, if you integrate, it will be 1. So what are the impact of this thing?
So we can do that by
yes,
changing from Cartesian to polar.
You can do it from Cartesian to polar.
So once we do e to the power minus x square by 2, and then we have e to the power minus y square by 2, we multiply that, we get e to the power minus r square by 2. So
yeah, so just
integrate.
let me, you tell me, I will. So if I consider c equals to integration minus infinity to plus infinity e to the power minus half x square dx. So c square I can write integration from minus infinity to plus infinity e to the power minus half x square integration minus infinity dx 2 plus infinity e to the power minus half y square dy. Right, this is what you are
So
saying,
now
right?
we change it. Yes, sir.
Yeah.
Now we change it from Cartesian to polar. We get 2 pi into that integration line. 1
Yeah,
by 2
so
pi
e
into
to the
that.
power minus half x square plus y square dx dy. Then from Cartesian x equals to r cos theta, y equals to r sin theta, r is positive and theta 0 to 2 pi. Okay. Now if you do this transformation, what you will get? Integration 0 to 2 pi, integration 0 to infinity e to the power minus r square by 2 r dr. So Jacobian, if you calculate, it will come as r dr d theta. So again integration from 0 to infinity to the power minus r square by 2 r dr. This integration will become 1 and the other part will come as d theta 0 to 2 pi. That will so this is 1 into 2 pi. So that implies c equals to root 2 pi. Well, this is just a mathematical trick or standard way of doing integration, but it has some statistical significance. You remember that from whatever we have so far done, we have started from uniform distribution and we have got other distribution. So from uniform to Bernoulli and from Bernoulli to rest of all of the geometric Bernoulli binomial, geometric negative binomial, all those stuff we have got. Poinsot as a limiting Bernoulli we have got. Discrete uniform we have got from continuous uniform. Then from uniform to exponential is exponential to gamma, gamma to beta. That also we have got. But for normal, to generate one normal random number, you cannot get from one uniform random number. You need two. And that method, the method by which you can generate a pair of normally distributed random variable from a pair of uniformly distributed random variable. 1 to 1 is not possible. And that method which transfers, say, U1, U2, their IID uniform 0, 1, from here transforming x1, x2, which are IID normal 0, 1. This transformation is possible. One only from U1 to x1, U2 to x2, that is not possible. You need a pair. So you need a pair. Need a pair. And this method is known as a Box-Muller method. We will demonstrate it after few construction. This is known as a Box-Muller method, and to how the Box-Muller method works, the underlying mathematical logic is this. We will come back to it and we will tell you that why this thing will help us to develop the Box-Muller method. But let me remind you that for one uniform random variable you cannot get one normal random variable. You can go from a pair to a pair. So this is possible. That method is known as a Box-Muller method, and to develop Box-Muller method we need this calculation as a background. So that's why I have just introduced this method of calculation. Otherwise you can go by the gamma integration, and also you can prove that this integral is 1. That is also a possibility, but this has a statistical significance. Okay. Well, so now before seeing it or talking about anything else, let us see what are the impacts of this mu and sigma happens to normal 0, 1. Let us try to see in the diagram. So this is the graph of normal 0, 1, 1000 samples generated. This is the graph of normal 0, 1. The red one is the true PDF, and from data the histograms are plotted. Now I am doing these changes. Let us consider in this way that y is same as this normal 0, 1, y1 is same as, y2 is location change by 2 and scale change by 0.5, and y3 is location change by -3 and scale change by 1.5. So location I have taken positive and negative, scale change I have taken greater than 1 and less than 1. So scale change for y2 is less than 1, scale change for y3 is greater than 1, location change for y2 is positive, location change for y3 is negative. Now you see the graph. If this is your standard normal, if you location change to positive, it will take to the same location as much you have changed. But as you have scale change with magnitude less than 1, it will squeeze the distribution. Again, if you do the location change is negative, it will take to the same location. But if you do the scale change which is greater than 1, it will inflate the distribution. So is it clear? Anybody has any query? So this is how the mu and sigma effect on normal distribution. So if you increase the value of sigma more and more, then it will be more and more inflated. If you decrease the value of sigma, it will be squeezed. And if you do the amount of location change, the same amount of location change will happen to the mean. So here, from here, you can see that for y1, from sample, the computed mean is very close to 0 because it is 0, and its standard deviation is very close to 1 because the true one is 1. But for y2, the mean is 2 because we have done 2 plus 0.5 into x1. So mean is 2 and variance is, or standard deviation is 0.5 because here sigma multiplied as 0.5. Similarly, here you can see this is very close to -3 and this is very close to 1.5. So from here, another important observation that you can have that so expectation of z when z follows standard normal, expectation of z equals to 0, variance of z equals to 1. How? You need to prove. But can you tell me what will be the expectation of x? So you can say x equals to this. X equals to this. X equals to this. X equals to this. Mu. And what will be the variance of x?
Sigma square.
Sigma square. Very good. But how you get this thing, expectation of z equals to 0? So normal distribution is one such distribution. Mean and variance completely characterize the distribution. If you know the mean and variance, you know everything about the normal distribution. So how can you conclude that expectation of z equals to 0?
So it is symmetric distribution.
It is a symmetric distribution around 0, or if you write down its expectation, so expectation of z, so it is integration minus infinity to plus infinity, z e to the power minus z square by 2 root 2 pi dz. It is an odd function. So odd function, if you integrate, you will get 0, provided expectation exists. As for variance, you need to calculate expectation of z square, and you will get the thing as 1. So there is not a very big deal about it. So now, before we go any further, let me tell you few properties of normal distribution, which are important properties. Yeah. So, well. So, normal 0, 1 is known as the standard normal. PDF of normal 0, 1 is denoted by this small phi. This is very much standard, okay, in statistics literature. And capital phi x denotes the integration up to x of this PDF, small phi. So this is the CDF of standard normal. It doesn't have any closed form. And already we have demonstrated that if z follows normal 0, 1, y equals to mu plus sigma z, then y follows normal mu sigma square, expectation of y equals to mu variance over. And PDF of y you can write in this form, that 1 upon sigma small phi of y minus mu by sigma, in this way. Small phi is a symmetric function around 0, so it is small phi of z equals to small phi of minus z, and this property holds from the symmetry also. And this is the property. Let us try to see with a diagram. So let me. So normal distribution usually look like this bell-shaped curve. It's a very nice, well-behaving distribution. So, by the way, you have not replied me. Example of normal distribution? So, this is the mean 0 standard normal. This is small phi x. So, this much is small phi of x, and if you go by symmetry, minus x, this is small phi of minus x. They have the same height, that is already told. And what is given, so if you integrate, say, from this point up to infinity, so this quantity, as this expression says, that small phi z is 1 minus phi z. So suppose this is z, so capital phi of z is from minus infinity to up to this point. So this is capital phi z, and this black region is 1 minus phi z, and that this black region, because of symmetry, this, if you call this is minus z, then this black region is same as this black region is phi of minus z. Is it okay? Anybody has any query? If this is z, this region is 1 minus phi z, and this area under the curve is same as this area under the curve, and this area under the curve you can write as capital phi of minus z. All these things hold because of symmetry. And if we write that z follows normal 0, 1, then probability z less than 1.64, these two numbers are very much approximately 0.95, and probability z less than equal to 1.96, this is close to 0.975. Okay, so 95th quantile is 1.64, 97.5 percentile, or that is the thing, that is 1.96. These two numbers are very much useful when you will do the statistical testing. And another important, I think I don't have here. Okay, so another important thing is this, that within 3 sigma limit, so if x follows normal mu sigma square in general, then x mu plus 3 sigma, mu minus 3 sigma, within this range, it will be very much approximately 99.97%. So it is very highly likely that most of the population or most of the distribution will hold within 3 sigma. If you go by 4 sigma, it will be going very close to 1. Okay. So what? Now you tell me the example of normal distribution. Example of normal distribution. So here, according to this one, so if it is 1.64, then this region is 0.05. One example from normal distribution.
So maybe mark distribution of a test.
Marks distribution of a test, oh, it will be, but for that you need a very large population. So already your test score from first test and second test, they have not come symmetric, they have come negatively skewed. With 1400 students approximately, it has come negatively skewed, it has not come symmetric. That much I can say. So population with more score is more.
Sir, probability that a missile hits the target at the distance of y.
Okay, so yes, that is one interesting one. So, hitting target or the distance from target, right? You want to say?
Yes, sir.
In a shooting competition or something like that. The very common and standard example of normal distribution is the measurmental error. So when you do all these physics experiments, measure with screw gauge, measure with different machines, so from the true how much error you are committing, so measurmental error is one of the very clear example where you can have positive error, where you can have negative error and all those stuff, and you can fit normal distribution to it very easily. Now other examples, you can have say height distribution, weight distribution, all those stuff you will be seeing in natural life that we are using normal distribution to model them. But well, measure error can be positive, negative, distance from the target you can also measure in a positive, negative sense, but height cannot be negative, weight cannot be negative, but still normal distribution holds good for them. For that, why that holds, this is the reason. The effective range of the distribution need not go to the negative numbers. within 3 sigma or 4 sigma limit, you can have the entire population. None of the human being has negative height. But if you fit a normal distribution within 3 sigma, 4 sigma limit, all the population will be there. So that is the beauty of normal distribution. And another thing that I have already told, I am repeating, that we will see when we will study the central limit theorem, that when population gathers in the number of population increases for a species in the nature, then the variety or the uncertainty, nature tries to increase the uncertainty, and when the uncertainty is more, then the vulnerability of the species is less. And the normal distribution is such a distribution. If you fix the mean and variance of a distribution, then normally distributed random variable has maximum uncertainty or entropy. So because of that, as an application of central limit theorem, many distribution can be converged to normal distribution. So theoretically and as an application, it has a huge impact. So gradually we will explore that. So I think it is the time to close it. Any query before we leave? Any query? Okay, if not, then thank you. See you in the next week. Thank you.
Thank you, sir.
Thank you. Thank you. You people also play with the code, copy paste in any R software interface and try to run those codes. You will change the parameter values and see how the distributions are changed. That's why I have given you the code. The code is not a part of this course, but being an IITian, you must be able to handle it. So there will be no question from the code, but for your experience, better experience, I have shared it. You copy paste those code in R window, so whatever interface you want, you use there, and try change the parameter values, number of sample size, and see the diagrams how they changes. That will increase your understanding. Okay, thank you. See you in the next week.
Thank you, sir.